All right, so I'm going to be covering 3.4a, using derivatives to describe the motion of a particle. So we're going to be covering this topic quite a bit throughout the year, and so this is our intro. So basically what you have to think about is if you have a ball, this is a simple scenario. If you're holding a ball and you're tossing it up and it comes back down and you catch it, and you toss it up and it comes back down and you catch it, let's say that your hand, the distance between your ball and your hand would be at 0. And as you raise the ball up, its distance is going to change from your hand. So any of those positions of distance away that the ball would be from your hand would be considered a position. The typical notation used for position is S of t. And this function will tell you the location or position of the object at any given time greater than or equal to 0. So for instance, let's say, here's an example. Let's say that your function is S of t equals t cubed minus 2t plus 3. And if I asked you, what is the ball's initial position? So let's say the time started at some point, not necessarily when the ball's in my hand, but at some point a time starts to measure the location. So the initial time, we would put a 0 in here, initial position. So I would then plug in this 0 everywhere, and I would end up getting that my initial position is 3 feet. So that's when the time started. The ball was 3 feet away from my hand. All right, so velocity, that tells you the rate of change of the position over time. So the notation for velocity is v of t, or because velocity measures the rate of change in position over time, that means the velocity function is the derivative to the position function. All right, so if here's my position function here, my velocity function would be 3t squared minus 2. And let's say since this original one was feet, then that means this would be feet per, let's say feet per second would be the units, because that's measuring how the distance is changing over time. So if I wanted my initial velocity, I would put v of 0, and I would get negative 2 feet per second. So what you also need to understand is if your velocity has a positive value, so if v of t has a positive output, then that means the particle, or in this case the ball, the object, is moving in a positive direction. So that would be like up or to the right. If my velocity value is negative, so my outputs, my rate of change in my position is negative, that means the object is moving.
Or press pound for more options.
In a, I don't know what that was about, in a negative direction.
To send this message, press pound
Isn't
or
that
hang
nice?
up. To play it, 3. To re-record it, 4. To add to it, 5. To discard it, 6.
Okay. I had to pause until all that gibberish was turned off. Anyway, acceleration. Acceleration measures the rate of change in velocity over time. So that means acceleration then is the derivative to your velocity. And it typically uses the notation a of t, or you could say the derivative to the velocity function. So in this case,
Martin Daly, student Martin.
Okay. So the acceleration function, if this is my velocity function here, my acceleration function is then 6t. And my units this time is going to be feet per second per second or feet per second squared. All right. And in this case, your initial acceleration would be 0 if you plug in a 0 in there. All right. And then lastly, we've got speed. Speed and velocity are very much related. Speed doesn't take into consideration the direction of the object. Velocity does. If you have a positive velocity, you know the object's moving in a positive direction or up or right. If your velocity is negative, then we know our object is moving in a negative direction or down or left. But speed doesn't consider the direction, just wants to know what the rate of change is. And so speed is the absolute value of your velocity.